So to everybody that keeps saying that it would be a good idea if teachers walked around schools armed, on behalf of, now I'm not going to say all teachers, but I'm going to go out on a limb and say a big majority of us, that's a terrible idea. So let's not even get into the weird logistics of the solution to the problem, as more the things that might be causing the problem. You know, hey, we keep we're eating food in the living room, and that's bringing in ants. What should we do? Eat more food. That'll take care of it. I mean, don't even talk about that. Just, you've probably got a yearbook in your house, no matter what age you are. Yours from high school, yours now, yours, your kids. Go get it. Open it up to any page. And just look at that smiling little teacher in the upper left corner and imagine them with a Glock. And even in college, you know, I'm in a department full of math and science nerds. And you know, we were that like way before nerd was like even close to being anything cool. I grew up in the 80s, and it was until I was 12 when I realized that fag didn't mean somebody who was into science. Hey, does anybody want to play Dungeons and Dragons? Oh, what are you, a fag? I don't know why my classmates sounded like truckers, but anyway, math and science teachers, we got decades of just repressed emotions from being laughed at and mocked and ignored by the opposite sex. We should not have sidearms. And over at the humanities building, where you got the English and philosophy majors, Jesus, those guys, I mean, they're either on the sort of the pussy end of the spectrum, where if you give them a weapon, they're just going to accidentally shoot themselves in the face. Or they're over on the other end of the spectrum, you know, the Hemingway and Hunter Thompson types that are going to intentionally shoot themselves in the face. So thanks, but no thanks. You dumbass. You know, the sad thing is that no matter what semester you're watching this, it's probably relevant, but I don't know. So for the general one, folks, we're going to talk a little bit more about ideal gas laws and some of the applications you were probably taught in the gas chapter. And for the general two, folks, we're going to do some ice table problems, because you can never do enough ice table calculations. So starting off with the general one, guys, let's take this example. Say you have an 8.8 gram sample of a gas. The volume is about 733 milliliters. Temperature is 22 degrees, and it's at a pressure of 1.1 atmosphere. That's your typical setup to figure out or to determine what the molar mass of this gas is. So, you know, you got volume, or not volume, you're talking about, you know, it's a gas, and you got a pressure and temperature. All that screams ideal gas law. So if you compare what's in the ideal gas law to what's given in the problem, you know, we're given a pressure, we're given a volume, we're given a temperature, and we know what the gas constant is. It looks like we have everything we need to find the number of moles. So you think, well, how is that going to help us? Well, notice that we're also given the mass, and molar mass is in grams per mole, as we're taught a few chapters ago. So if you have, we already know the mass. If we can figure out how many moles we have, we can use that to find molar mass. So you take all the other stuff that's given and you plug it into your ideal gas law and solve for N. And remember the one sort of trick here, if there's a trick, you know, no matter whatever the units are given in the problem, make sure they match the units of the gas constant. So you notice we converted milliliters to liters. And was it other temperature we converted to Kelvin. So you plug all that in and you get 0.033 moles. So now we have the mass, now we have the amount in moles. You divide the two, you get 265 grams per mole. A related problem that you're probably taught is to find the density of a known gas. And you'll see in a minute why it has to be known. But let's try to find the density of carbon dioxide at 294 Kelvin and 0.95 atmospheres. So again, you see pressure, you see mention of a gas. If you look at everything that's given, we're given a pressure, a temperature, and we know the gas constant. So we have everything we need to find, actually, volume, neither actually, because we still don't know the volume or the amount. So it's kind of hard to do a algebra type equation where you have more than one unknown. But yeah, we know the identity of the gas. Skip slide. So we know it's carbon dioxide, and we know the molar mass of carbon dioxide is 44.01 grams per mole. So that means 1 mole of carbon dioxide is 44.01 grams. So we know the mass of a mole. Let's use the ideal gas law to find the volume of 1 mole. And again, make sure your units match the gas constant, and here they all do. So if you plug in 1 mole for N and you solve for V, you get 25.4 liters. So we know the mass of a mole, we know the volume of a mole. You divide the two, you can find a density in grams per liter, which in this case would be 1.73. And it doesn't matter what amount you pick. I mean, a mole is, we just pick 1 mole for convenience sake, since you know the molar mass, you know how much 1 mole weighs already. Because remember, density is an intensive property, going back to chapter 1. So, but again, you have the mass of a mole, just use the ideal gas law to find the volume of a mole. And notice in both examples, we start with the ideal gas law. So again, if you see anything related to a gas, especially if you see temperature, pressure, all that other stuff, especially at this point in Gen Chem, all that just screams ideal gas law. So when in doubt, start with the ideal gas law and see where that takes you. All right. So for the general 2 guys, this is the time we're still kind of working on equilibrium, and this is the time where we really start to get into ice tables. And I've said it before on other shows, ice tables are kind of like the stoichiometry of, or really equilibrium in general. It's kind of like the stoichiometry of General 2. You know, in General 1, once you started stoichiometry, it just never went away for a while until you got to electron arrangements. Equilibrium is kind of the same thing. And so a lot of times when you're doing equilibrium type calculations, you tend to start with an ice table. It's kind of a nice little systematic way to set things up and figure out how to calculate whatever it is you're trying to calculate. So do a couple examples from there. Excuse me. Let's look at the reaction between hydrogen and fluorine to give you hydrogen fluoride. And let's say the equilibrium constant is 0.56. Maybe it is, maybe it isn't. I just made that number up for purposes of this problem. I do that a lot. But let's try to figure out what the equilibrium concentrations are if you start with 0.5 molar hydrogen and 1.2 molar fluorine. So kind of like with the ideal gas law, or ideal gas law problems, or just problems involving gases, you know, when in doubt, start with PV equal nRT. If it's related to equilibrium, you know, when in doubt, start with an ice table and see where that takes you. So we'll start with our reaction and its chemical equation, and we'll work on an ice table. So remember, ICE stands for the 3 types of concentrations we're doing. I is our initial concentrations, and those are given in the problem. All right, we're told we're starting with 0.5 molar hydrogen, 1.2 molar of fluorine. Didn't say anything about starting with HF, so we'll assume we're not starting with any. And if we're not starting with any product, then it's going to have to shift to the left, which means during the, or to the right, excuse me, shift to the right. So we're going to lose some amount of hydrogen. And for every X amount of hydrogen we lose, we're going to lose that same amount of fluorine, since it's 1-to-1. And since we have two products for every one hydrogen and one fluorine, for every one reactant we lose, we're going to lose two, or we're going to gain two equivalents of product. So for row C, our change in concentration, remember the plus or minus comes from the shift. You know, the minus is the side it shifts away from, the plus is the side it shifts to. And the best way to figure out the magnitude of X, whether it's 1X, 2X, 3X, is just pull it straight from the coefficients. That's the easiest way to handle that. And row E is just basically adding the other two rows together. So at equilibrium, we're going to get 0.5. We're going to have 0.5 minus the X we lost in the shift. Fluorine is 1.2 minus the amount we lost in the shift. And for our product, it's however much of that 2X we gained from the reaction. So other thing we're going to use is our expression for K. So it's product over reactant, raise everybody to a value equal to its coefficient. And we're just going to plug in row E into our expression for K. And from there, you solve for X. Oh, I forgot to add, we're also plugging in our value for K right here, as you can see. But from there, you know, you solve for X. So the way that we start solving for X here is we have to combine the two things at the bottom. So you have to remember the FOIL method from an algebra class. And when we apply the FOIL method, we get this bit at the bottom. Then we can, you know, multiply both sides by the bottom, you know, which effectively moves it to the left. Multiply 0.56 to all of the stuff in parentheses. And eventually, you know, we start to make, as we fiddle with this equation, we can get something that looks like this, which you might remember is a quadratic equation, where in this case, A is negative 3.4, B is negative 0.952, and C is 0.336. All right. So you gotta break out your math notebook, or actually it's usually in your chemistry book too, because this comes up a lot in this chapter. Or you just their website, you can plug it in online. But remember, the way you solve for a quadratic is you use this weird equation, and you plug in your A, B, and C, and you get two possible values, since at the top we have a plus or minus part there. So X can either be negative 0.48 or 0.203. But what you usually find is that one of these values is not possible because it gives you a negative concentration. In this case, if you look at 0.48, then that means our product concentration is going to be negative 0.96. And you can't have a negative concentration. That's like saying you weigh negative pounds. So 0.203 should be the one that works. And I've done a lot of these kind of problems. I don't ever remember seeing one where both of them are valid. Yeah, usually one, I mean, what you're going to find is one of them should give you a negative concentration, and that's the one you kick out as an impossible answer. So X is going to be 0.203. So looking at row E, hydrogen's concentration should be 0.5 minus X, which makes it 0.3 if you round back up to sig figs. Fluorine's concentration is going to give you a concentration of 1. And these are all in molarity. I forgot to go back and add the M. And again, hydrogen fluoride is going to be 2x, which means this concentration is 0.406 molar. And remember, the way you can check your answers here, which is especially helpful when you're doing this kind of quadratic based kind of stuff and the FOIL method and all that, easy way to check your answers is to just take these concentrations and plug them back into your expression of K. And what you should get is something really close to the K that was given to you in the problem. So here we get a K of 0.55, which is reasonably close to the K that was given, you know, factoring all the rounding and whatnot that we had to do to get down to this value of X. When you're off, you know it. And actually, confession, when I was putting this problem together, I screwed up. You remember the little 2x squared bit? I forgot to square the 2. And when I did my check, I ended up getting a K of 1.2. So yeah, I knew I screwed up somewhere. So I just had to go back and go through every one of those freaking lines, which is kind of a pain, admittedly, and figure out, oh yeah, it was 2x squared. I just did, you know, I didn't square the whole thing. So again, always check your work if possible. And again, easy way to check your work there is to just plug your concentrations back into K and see if you get the K that was given. So looking at another example, let's look at this reaction where carbon monoxide decomposes to carbon and oxygen. And let's say that this is our equilibrium constant. Let's find out what the equilibrium concentration of oxygen is going to be if we start with 2 molar carbon monoxide. So we start with the equation and we work on our ICE table. And for row I, again, we're given the concentration there. Carbon, we're not going to worry about carbon because it's not part of the expression for K. So, you know, because it's a solid. Remember, solids and liquids aren't factored into the expression of K. So, yeah, don't even worry about carbon for this question. You know, this is not important. But yeah, we didn't say anything about starting with some amount of oxygen, so we'll assume there's not any there. So as before, it's going to shift to the right. I guess I should have flipped this one around so it shifted to the left, but that's okay. There are other ones I've done in other videos where that happens. So it's going to have to shift to the right. So again, we're going to lose some reactant, gain some product. And to figure out how much, just make your X equal to the coefficient. So we should lose 2X worth of carbon monoxide and gain X amount of oxygen. So at equilibrium, it's going to be the initial amount we had minus the amount we lost during the shift. And for oxygen, it's going to be whatever X amount you gain. Right. So like before, we take row E, plug it into our expression of K. And again, we plug in our value for K into K. And we start to solve for K. And for this one, you might start to do a quadratic because it looks like that's the kind of problem we're going to end up running into. And I guess you can use a quadratic if you want. You should come up with an answer. But you don't have to do a quadratic every time it looks like you might have to do one. For this one, we can actually get around it based on the fact that we have a really small value of K. All right. Which means it's going to shift. I mean, so it's a small value, which means it's reactant favored. And it's really, really small. So at equilibrium, it didn't shift a lot. So at equilibrium, it looks like a big chunk because remember, equilibrium constants a ratio of product over reactant. So if it's that small, that means at equilibrium, it's a lot more carbon monoxide and oxygen once you reach equilibrium. So it had to shift to the right to make some oxygen, but if it's that small of a number, it didn't shift a lot. And it was probably such a small shift, we can we can, it's what we call solving by approximation. Since it looked like it was such a small shift, we can just substitute or approximate 2 minus x to just 2. And that makes solving for x a whole lot easier, because you just essentially have to multiply both sides by 4 to get a value that is 1.7 times 10 to the negative 7. So going back to row E, or what's actually, I jumped ahead, didn't I? As far as like whether or not it was okay to approximate, I knew I'd jump ahead at least once or twice. We use what we call the 5% rule, which 5% rule isn't really a, it's not a chemistry thing. It's more of it's a math thing. Because remember, every measurement you make has some degree of error. It's plus or minus. Every graduated cylinder says, plus or minus whatever. Every balance says, has, plus or minus 0.01 grams, or however many digits your scale can go. So there's some natural acceptance of some error. And so as a general rule, most people say that as long as your error is not bigger than 5%, you're okay. So it means you can be 95% accurate and you're good. So what that usually means for ice table problems and approximation is that whatever term you removed by approximation, it has to be less than 5% of the thing you removed it from. So in this case, 2x has to be less than 5% of 2. And in this particular case, you probably don't have to do the math to see that, 2 times x is a lot smaller than 5% of 2. 5% of 2 is only 0.1, and we're way lower than that. So the 5% rule works here. If you actually go back to the other problem we did, it would have failed. So you would have had to do it the long way with the quadratic equation. But in this case, the 5% rule is okay, and it looks like our value of x is acceptable. So now we take row E and use that to figure out our equilibrium concentrations. And for carbon monoxide, like we kind of predicted before, if you plug in x into row E for carbon monoxide, you get 1.99983, which, if you round back up to 2 sig figs, makes it 2. And oxygen is whatever value x is. And we can check our work like we did before, just plugging in our values that we just come up with, and we can leave the approximated value for carbon monoxide, and yeah, you get the given value of K. So and one way to kind of early on, before you actually start doing any math, to see whether or not it's going to be okay to approximate or not, is to kind of compare your initial concentrations with the size of your K, the value of K itself. The bigger the difference is between those two, your initial concentrations and K, the more likely approximation is going to work. So like in that last example, K was on the order of 10 to the negative 8. Our initial concentration was, I think, 2. So that's the difference, but they differ by a factor of 1 billion. So when the difference is that big, approximation is probably going to work. And we saw it was well below the 5% rule. For the one we did before, I already forgot the values, but our K was like what, 0.556? Or is that what it used to be? Where's that? Yeah, 0.56. And the initial concentration was 0.5. So they were the same. They were both, point something. They're actually both 0.5 pretty much. So yeah, when those two values are that similar to one another, probably approximation is going to fail. So don't even bother. Sometimes you get kind of a gray area when they differ. One example we did, they were pretty much the same order of magnitude. The other, where they were differed by 1 billion. The gray area is when the two are different by a factor of, 10 to the 4, 10 to the 5, 10 to the 6, that kind of range, especially 10 to 4, 10 to the 5. In those cases, it might work, it might not. What I usually tell students is go ahead and try it, because if approximation works, you've saved yourself a lot of time. If it didn't work and the 5% rule fails, you didn't really lose a lot of time. So the whole risk reward of giving it a shot is usually worth it. All right. So that's it for this show. Next week, I'm not going to have some kind of weird political rant. Maybe. I don't know. As we're watching this, we're still in primary debate season, so I don't care, honestly. I mean, really, nobody you see in those debates right now, and right now it's like late 2015. They don't want to be president. They're just trying to increase their appearance fees. So it's like anybody else on the internet. Just ignore them and don't engage. Except for me. You can engage me all you want. Not to argue about what I said at the beginning. Just, I don't care. But if there are things that, you're talking about in class now that you want to talk, you need help with, or want to see examples that instead of the stuff that I'm planning on doing next week, whatever it may be. If you have any suggestions for things to go over, then just visit my channel and put it in the comments. I don't do comments for videos. There's just too many videos for me to have to deal with. But yeah, right now my channel page is still has comments open. So go ahead and tell me if there's something else you want to look at. Or if you're one of my students, you have my work email address, just do it that way. So that's all, folks. Oops, I missed the stop broadcast button. That's all, folks.